Hello everyone. In this video we will learn about the cyclic quadrilateral and its properties with their proofs. First of all, we should learn what a cyclic quadrilateral is. See, here we have a circle and we are having 4 points A, B, C and D which are lying on the circumference of the circle. Then the quadrilateral which is formed by joining these points is the cyclic quadrilateral. So how can we define it? We can define it if all the vertices of a quadrilateral lie on a circle, then it is known as a cyclic quadrilateral. Or because we know that all the points which are lying on the circumference of the same circle, they are also known as concyclic points. So we can also define it as a quadrilateral which is formed by joining 4 concyclic points is a cyclic quadrilateral. Like we can see here, A, B, C, D is a quadrilateral and its all the 4 vertices are concyclic. Therefore, A, B, C, D is a cyclic quadrilateral. Now we discuss about the properties of cyclic quadrilateral, and the first property is the sum of the interior opposite angles of a cyclic quadrilateral is 180 degree. We know that the sum of 2 angles is 180 degree. They are known as supplementary angles. So we can also say that a pair of opposite interior angles of a cyclic quadrilateral is supplementary. How to prove this? First we have to draw a diagram. A diagram is here. A cyclic quadrilateral A, B, C, D. O is the center of the circle. What is given to us? A cyclic quadrilateral A, B, C, D. What we have to prove? We have to prove that angle A plus angle C is 180 degree and also angle B plus angle D is 180 degree. Construction. We need a construction here. We join the center to the vertices B and D. So we write join OB and OD. Now we come to the proof. For the proof, we can remember one of the theorem that the angle subtended by an arc at the center is twice the angle subtended by the same arc at the remaining circumference or at any point of the remaining circumference. By applying that particular theorem, we can write by arc DAB, angle 1 is at the center and angle C is at the remaining circumference. This is equal to twice of angle C. And the reason they can write angles by same arc. This gives the reason that they are the angles subtended by the same arc. This we can write as number 1. Now by arc BCD, by arc BCD, angle at the center is angle 2 and the angle at the remaining circumference is angle A. So we can also write angle 2 is equal to twice of angle A, and the same reason can be given for this, and this we can write as 2. Now by adding them, by adding 1 and 2, we can get angle 1 plus angle 2 is equal to twice of angle C plus twice of angle A. If we take 2 common, this is twice of angle C plus angle A. And we know that angle 1 and 2, if we add, that is an angle of 360 degree, complete angle. So we can write this implies that 360 degree is equal to twice of angle C plus angle A. So what we get about angle C plus angle A? That will be 360 divided by 2, that becomes 180 degree. Now, either we say similarly we can prove that angle B plus angle D is 180 degree. Or we can also say that we know that sum of all 4 angles of a quadrilateral is 360 degree. Therefore, the sum of B and D will be 360 minus 180. and that will be 180 degree. So we can also write here, similarly, we can prove angle B plus angle D is also equal to 180 degree. And that's what we have to prove. Hence, proved. So like this we could see that the sum of opposite interior angles or sum of a pair of opposite interior angles of a cyclic quadrilateral is 180 degree. The second property of theorem is that if there is a quadrilateral in which a pair of opposite angles is supplementary or have a sum of 180 degree, then it is a cyclic quadrilateral. How to prove it? First we draw the diagram in which ABCD is a quadrilateral in which angle A plus angle C is 180 degree. So given a quadrilateral ABCD in which angle A plus angle C is equal to 180 degree. To prove, we have to prove that ABCD is a cyclic quadrilateral. It means all the four vertices of this A, B, C and D should lie on the same circle. Then we need a construction here. In construction we consider that the quadrilateral is not cyclic. Suppose the point C is either lying outside the circle or it is inside the circle. In case of outside the circle, suppose we find that DC is intersecting the circle at E, then join BE. In the second case, we produce DC and suppose it meets the circle at E, then join BE. So in construction we write, suppose ABCD is not a cyclic quadrilateral, then draw a circle passing through points A, B and D. Then there can be two cases. Number one, C lies outside the circle and DC meets the circle at point E or intersects the circle at point E. Join B. The second case, C lies inside the circle, then produce DC to meet the circle at E and join BE. That in both the cases. Now we will come to the proof. The proof is, by construction we find that ABED in both the cases is the cyclic quadrilateral, and we know the sum of opposite interior angles of a cyclic quadrilateral is 180 degree. So we can write here, in quadrilateral ABED, angle A plus angle E is equal to 180 degree. The reason is opposite angles of cyclic quadrilateral. But we are given that angle A plus angle C is 180 degree. We can write here, given angle A plus angle C is equal to 180 degree. This is suppose 2 and this we can write as 1. What we get from 1 and 2? From 1 and 2, we get angle A plus angle E is equal to angle A plus angle C. This implies that angle E is equal to angle C. Now the thing comes here, angle E here is the exterior angle of triangle EBC. Here angle C is the exterior angle of the triangle CBE. And we know that exterior angle of a triangle is never equal to its opposite interior angle. So we can write here, but this is not possible because exterior angle of a triangle is never equal to its opposite interior angle. Therefore, angle E is equal to angle C only if C and E coincide. And if they coincide, it means all 4 points lie on the same circle. So we can write this implies that A, B, C, D are concyclic points. And if they are concyclic points, then A, B, C, D is a cyclic quadrilateral. This implies that A, B, C, D is a cyclic quadrilateral. And that's all we had to prove. So we could learn how to prove that a quadrilateral in which a pair of opposite angles is supplementary is a cyclic quadrilateral. The next property is the exterior angle of a cyclic quadrilateral is equal to its opposite interior angle. See, here we have been given a cyclic quadrilateral ABCD. Its one of the side is produced to form an angle CBE, that is exterior angle of it. And we have to prove that this angle is equal to opposite interior angle, that is angle D. So what is given to us? A cyclic quadrilateral ABCD. AB is produced to E. So angle CBE is an exterior angle. And we have to prove that angle CBE is equal to angle ADC. There is no construction required in this. So we are coming to the proof directly. We know that a pair of opposite interior angles of cyclic quadrilateral is supplementary or have a sum of 180 degree. We can write here the same. We know that the sum of opposite interior angles of a cyclic quadrilateral is 180 degree. Therefore, angle ABC plus angle ADC is equal to 180 degree. But what we see here, that this angle and this angle also have a sum of 180 because this is a linear pair. We can write, but angle ABC plus angle CBE is equal to 180 degree, that is number 2, and we can write the reason, it is a linear pair. What we get from these two? That these two are equal. So we can write from 1 and 2 we get angle ABC plus angle ADC is equal to angle ABC plus angle CBE. This angle ABC and ABC cancel each other. So are we getting that angle ADC is equal to angle CBE? It means the exterior angle is equal to the opposite interior angle, and that's what we have to prove. Hence, proved. So we could prove this theorem also, that the exterior angle of a cyclic quadrilateral is equal to its opposite interior angle. Now we shall discuss one of the example based on the application of cyclic quadrilateral. And the example is that we have been given a figure in which there is a quadrilateral ABCO. AB has been produced to D, and it is given that angle AOC is 100 degree. We have to find out angle CBD. We can make use of cyclic quadrilateral to find the solution of this problem. So what we do in the solution, we take a point P in the remaining circumference and join AP and CP to form an angle APC. So we can write here, take a point P in the remaining circumference and form angle APC. Now we know that by an arc, angle at the center is twice the angle at any point of the remaining circumference. Therefore, what we get here? Angle AOC is equal to twice of angle APC. Why? We can write here angles subtended by arc ABC. To make it more clear, we have not written AC, we have written arc ABC. Or we can also write this as arc AC. This is given 100 degree, equal to twice of angle APC. This implies that angle APC is equal to 100 upon 2, that is 50 degrees. And if this angle is 50 degree, now it is a cyclic quadrilateral. And we know that exterior angle of a cyclic quadrilateral is equal to the opposite interior angle. So we can write, since ABCP is a cyclic quadrilateral, therefore angle CBD is equal to angle APC, and that will be equal to 50 degree. We can write here exterior angle of a cyclic quadrilateral is equal to its opposite interior angle. That's the reason. And therefore we are finding angle CBD is equal to 50 degree. This is the answer to the problem. So in this video we learnt about a cyclic quadrilateral, its properties and the application of the properties in solving some of the problems. In the next video, we will learn about the tangents to a circle and the theorems based on it. Thanks for watching my video. If you have any comments or doubts, leave them in the comment box and I will get back to you.